So I've summarized this problem with this awesome picture. There's an airport, and 15 miles away is a bus depot. And this red bus leaves at, the yellow bus leaves first and leaves at 9 o'clock. And it's traveling at 30 miles per hour. And this red bus leaves at 9:05 and travels at 40 miles per hour. So the question is a lot of different questions. I'm going to answer all the questions in the textbook, hopefully, and a few more. So first, let's just look at this yellow bus. And if it's going 30 miles per hour over a 15 mile stretch, how long is it going to take to finish? So this is going to help us think about the scale of our problem. And if you do some mental math, if you just think, well, if I'm going 30 miles in every hour, how long would it take me to travel half that distance? It should take me half the time, which is 30 minutes. So that's what I'm going to put. I'm going to put minutes. Let me even mark that. 30 minutes right here. We are going, this is the yellow bus. At 30 minutes, we are going to be at our destination 15 miles away. So let's put that point right there. And the next thing is what I've also implied by this drawing is that the 0 minute corresponds, 9 o'clock corresponds to the 0 minute. Okay, it corresponds to 0 minutes. So and we know that at time 0 we're at the bus depot, and so it's going to be a straight line because we're going exactly 30 miles per hour. What's the slope of this line? The slope of this line is rise over run, 15 over 30, which is 1/2. And I think that's the answer to the first one. So distance here, this is distance. Distance as a function of time, and time is in minutes, is quite simply, for the yellow bus, distance is equal to the rise over the slope, 1/2, times, right, the rise is 15, the run is 30, so rise over run is 15 over 30, or 1/2, times the time. So if you gave me any minute time in here, if you said, if I said, where is it at t equals 20, right, so t equals 20 right there, you could use this right here and say, at t equals 20, we are at 10 miles, because you just put that right in there for t, and you could solve it that way. So let me get rid of some of those extra marks. Okay, and so that's the answer for the position. The distance is a function of time for the first bus. What about the second bus? Well, we're going to use some more algebra here. At time 0, the bus is still sitting there at the depot, and not until at the 5th minute does the bus leave. And what's the rise over the run? In this case, just like 30 corresponded to a slope of 1/2, because we found that this 1/2 is really the 15. Well, we sort of backed it out from the graph, so maybe we shouldn't do that. If 30 miles per hour is 1/2. Well, no, this should make sense. That this is really, this 1/2 is really 30 divided by 60, which here is the same as, which is really the same as this 15 divided by 30, right? Right. This is all 1/2. So really, we're taking the miles per hour and dividing it by 60. So here we have a slope. So let's write this. D is equal to, first we need the slope is 40 over 60 times t, but we don't know the intercept, and if we think it's going to go back like this, that's really what we're looking for. We're looking for this y-intercept, but we do have a point on this line. We do have it, so we have a slope. M is equal to 4/6, or I'm going to go right to 2/3, and we have a point. What point is it? It's 5, 0. Right, that's that point right there. So what's the equation of the line? We can use point slope now, and it's y. I shouldn't say y because our vertical axis is d. D minus 0 equals 2/3 x minus 5. So distance is equal to 2/3 times x minus 5. And I'm going to leave it like that for right now. We could get it in point slope, but I'm going to leave it like that for a reason. So the line's going to look just like this, and we're going to stop when we get to 15. We're interested in a lot of things. What time does the what time right here does the red bus reach its destination, and what time and distance? Where do the buses cross? So let's answer this question first. Well, here is the equation of our line right here. And we really want to know when the distance is equal to 15. So we're going to take 15 for distance, so that it's equal to 2/3 times x minus 5. You might see why I left this in this form. So what if we take both sides here and multiply by 3 halves? And I picked that number because the reciprocal of 2/3, and I know when I multiply here, these guys are going to cancel, and I'll be left with x minus 5. We'll be really close to isolating that x. And I should call it t. My apologies. And let's use a smaller brush here. Let's call this t. All these should be t's. It was t here. It should have stayed t's throughout. So there's t. And okay. So multiplying by 3 halves, we get 3 times 15 divided by 2. That's 45 halves. 45 halves is equal to t minus 5. So t is equal to 45 halves plus 5, and I'll just work this way for a second. 5 is the same as 10 halves. This is 55 halves. So this is going to be roughly 27.5. So this right here is 27. It's not roughly, it's exactly 27.5 minutes when we reach our destination. But what about when they cross? Well, that's when these two lines are equal. This is where we set. We know that d is equal to 2/3 t minus 5 for the red bus. D is equal to 1/2 t. We want to know where they intersect. So with these two, we can use straightforward substitution, setting, well, 1/2 t is equal to 2/3 t minus 5. And multiplying everything by 6, because we don't really love fractions. I mean, we like them, but we don't love them. 6 times 1/2 t is 3t. 6 times 2/3 is going to be 4 times t minus 5. Do not distribute that 6 over more than just one side. So we have 3t is equal to 4t minus 20. And if we subtract 3t from both sides and add 20, you can see that 20 is equal to t. So that's our time right here when they cross each other. And using either of these equations, we can find that the distance, or go right to this one. This is perfect. At what distance? T equals 20. What's 1/2 of 20? This is a distance of 10. Okay.